which distribute optimal intercept points, kill boxes to Skynex batteries. When a wave of Shaheeds appears from the northern border, the data is not shared only with Patriot or NASAMS. It is also passed to air defense gun batteries positioned tens of kilometers away. This is the strength of a layered system. What one tier misses, another captures. No target moves through the network unchallenged. Russia's attack patterns reveal exactly why Skynex became a structural pillar of this architecture. Russian doctrine typically begins with dozens of Shaheeds to saturate tracking algorithms and force Ukraine to expend ammunition. Only afterward do Kh-101 caliber or Kh-55 missiles arrive in the dead of night. This tactic depends entirely on the assumption that Ukraine must fire surface-to-air missiles at everything. But Skynex does not require missiles. It requires only programmable shells. Shaheeds are destroyed with bursts costing a few thousand euros. Caliber missiles are shredded with A-head rounds. As a result, high-end interceptors preserve their loadouts for genuinely strategic targets. This is why many NATO officers describe Skynex as the strategic filter of Ukraine's air defense network. This layered structure is further strengthened by older but highly effective systems such as Gepard, ZSU-23 Shilka, towed 23mm guns, Manpads teams, and mobile counter-UAV units. Though each system has limitations, when combined with Skynex they form an air defense labyrinth, a multi-layered web of sensors and engagement zones, each with a different cost structure. Russia attacks in waves, Ukraine answers in tiers. A target that bypasses Patriot faces IRIS-T. If it slips past IRIS-T, it encounters Skynex. Past Skynex comes Gepard, and beneath all of it lie Manpads and mobile drone hunting teams. This is why Ukraine's interception rate throughout 2024 and 2025 remained near 67%, despite constant changes in Russian tactics and flight routes. What shocked Russia was not only the interception rate, it was the economic inversion. Russia spends millions of euros on a strike package. Ukraine pays thousands to neutralize it. Russia deploys inexpensive decoys. Ukraine still intercepts them for less. Russia increases the number of drones. Ukraine increases only the number of shells. This is cost asymmetric warfare in its purest form, an equation with Skynex at the center. High-priced precision strikes collapse into budget-efficient defeats. And with European logistical support, 35mm ammunition is produced far faster than Russia can manufacture Ka-101 or Caliber missiles in factories across Tatarstan. The arrival of the Skyranger 35 pushed this strategy even further. Skyranger places the entire Skynex weapons package on a fully mobile platform, repositionable within minutes, capable of escorting mechanized brigades, guarding supply routes, or sealing blind spots that fixed Skynex units cannot reach. In this new structure, Skyranger becomes the mobile shield, while Skynex remains the static fortress. Both operate within the same radar network, forming a mid-low tier that can scale horizontally across the battle space. And this is the element Russia cannot easily counter. Not because Skynex is more powerful than Patriot, but because Skynex is cheaper, faster, harder to overwhelm, and scalable at a rate the Kremlin cannot match. Yet even such a capable system carries structural vulnerabilities, weaknesses on the battlefield that Russia is working relentlessly to exploit in every new strike cycle. No air defense system, not even legendary names such as Patriot, SAMP divided by T or IRIS-T, SL is perfect. Skynex is no exception. And to understand why Ukraine cannot intercept every Russian strike, we must look directly at the system's real battlefield constraints. These are the weaknesses Russia studies carefully, tests relentlessly, and tries to exploit every month, every night. The first limitation arises from Skynex's core design. It is a static system. The 35mm guns are truck-towed, deployed in fixed configurations, and require setup time, cable linking, and radar alignment. They guard high-value sites, airfields, logistics depots, power plants, grid control centers, and radar hubs. but they cannot accompany mechanized brigades or maneuver fluidly with the pace of mobile warfare. In high-tempo operations, where Ukrainian units relocate every few hours to avoid Lancet strikes or UMPK glide bombs, Skynex simply cannot keep up. Russia understands this with absolute clarity. Thus, it deliberately targets what lies outside the shadow of Skynex: supply convoys, forward command posts, brigade staging areas, and exposed logistics corridors across eastern and southern Ukraine. These zones often rely solely on manpads, 23mm guns, or small mobile drone hunting teams. Skynex cannot be everywhere. That geographic gap is exactly where Russia now directs the bulk of its precision fires, striking the seams between layers. The second limitation is volume of fire. Skynex is extraordinarily effective against individual cruise missiles, but when 10 or 12 low-altitude threats arrive simultaneously, the demand for firepower multiplies. Each engagement consumes dozens of A-head rounds. Even with large ammunition stocks per gun, there are logistical limits. A saturation attack lasting 5 to 7 minutes can force a battery to expend more ammunition than it can reload within a single engagement cycle. Russia is not unaware of this. To defeat Skynex, Moscow does not need to beat the radar, it only needs to outlast the magazine. This became evident during Russia's mixed strike packages in late 2024, Shaheds flying in upper-low altitude layers, decoys in the mid-band, and Kaliber missiles threading the lowest routes. Skynex was forced to prioritize targets, choosing which threats to kill and which to delay. In those same minutes, ammunition ran down rapidly. Even an excellent system must eventually face the cold arithmetic of war. No platform has infinite firepower. This reality shows clearly in Ukraine's overall interception rate, approximately 67% across all systems. It is an impressive figure, yet not absolute. No system, including Patriot PAC-3 MSE, can intercept every missile in a complex strike package designed to overwhelm multiple layers at once. Russia often pressures Ukraine with 3 simultaneous threat classes: drones, cruise missiles, and glide bombs. Even when Skynex delivers optimized bursts, some targets inevitably slip through small gaps within the layered structure, an unavoidable outcome in a continental-scale conflict. The third limitation is engagement range. Skynex is only truly effective in the last few kilometers before the target reaches its objective. It cannot replace mid-range and long-range defenses. If the target flies higher, changes altitude unpredictably due to GPS divided by INS distortion, or begins its descent only in the final minutes, the initial defensive burden still rests with Patriot, SAMP divided by T, and IRIS-TSL. Skynex is the insurance layer, not the primary one in the first engagement window. Yet, and this is what NATO strategists have been forced to confront, these limitations do not diminish Skynex's strategic value. Because Skynex was never designed to chase tanks, defeat hypersonic weapons, or shield maneuver brigades, its mission is simpler and more revolutionary: to make cruise missile warfare financially unsustainable for the attacker. Russia can launch a KH-101 costing several million euros, but if Ukraine destroys it with a few thousand euros and still has ammunition left for the next salvo and the next one, then long-range strike model Moscow has built for 2 decades begins to destabilize, and that is only the beginning. For while Ukraine reached this conclusion on the battlefield, Europe reached the same conclusion in its command rooms. NATO discussions in early 2025 revealed a truth few nations were willing to say publicly: an air defense network reliant solely on missiles is financially unsustainable. And within this doctrinal shift, Skynex, despite its limits, is becoming the conceptual center of Europe's future defensive architecture. But what happens when an entire continent begins acquiring a system Russia has no answer for? And what happens when Europe deploys not 10, but hundreds of Skynex batteries from the Baltic to the Balkans? The answer lies ahead in the next chapter, where Skynex begins transforming from a battlefield asset into a strategic standard for NATO. When Ukraine proved that Skynex could destroy Russian cruise missiles in real combat, the entire logic of European defense procurement shifted overnight. For years, NATO ministries had been fixated on long-range interceptor systems. Patriot, SAMP divided by T, Aster, Iris, T, SL, SM6. These weapons are extraordinarily capable, but also extraordinarily expensive, logistically heavy, and slow to manufacture. No government publicly admitted it, yet every planner quietly understood the same inconvenient truth. In a saturation strike modeled after Russian or Chinese doctrine, any missile-dependent air defense network would run out of interceptors long before the attacker ran out of munitions. Skynex shattered that logic in a matter of months. Romania moved first. After reviewing battlefield data from Ukraine, Bucharest ordered 2 Skynex batteries. Austria followed with a purchase of 7 batteries, despite previously investing almost nothing in low-altitude air defense. Then came Slovakia, the Czech Republic, and several nations that did not announce procurement publicly but quietly requested capability risk assessments from Rheinmetall. These were not marketing-driven purchases. They were data-driven, confirmed by Ukrainian crew reports, OSINT footage, satellite analysis, and technical evaluations by NATO expert teams. By mid-2025, a new consensus had begun forming inside NATO internal meetings. No nation can sustain an air defense architecture based exclusively on missiles. A single Patriot PAC-3 MSE shot cost between 2 and 4 million euros. Each Iris TSL launch cost roughly 400,000 euros. Meanwhile, Russia can force a defender to spend millions by sacrificing a Shahed drone priced in the tens of thousands. A Caliber or KH-101 requires only a cheap, unmanned decoy to trigger a wildly disproportionate defensive response. This is no longer purely military conflict. It is financial warfare, a form of economic attrition Russia inadvertently turned into a doctrine. Skynex arrived precisely when that doctrine began to collapse. With each burst of programmable ammunition costing only a few thousand euros, Skynex can handle the majority of low-altitude threats, UAVs, decoys, glide bombs, and subsonic cruise missiles, reducing the workload on medium and long-range missiles by 70 to 85%. The results are transformative. Expensive interceptors are conserved for expensive targets, financial attrition is reversed, and air defense becomes sustainable for the first time in 2 decades. From a doctrinal standpoint, the shift is seismic. NATO has begun adopting a new 3-layer model. The gun layer, low-cost intercepts for UAVs, decoys, and cruise missiles. The short-range missile layer for medium-value targets that cannot be handled by guns. The long-range missile layer for strategic and high-altitude threats. No longer is the gun viewed as secondary. In the new model, guns are the foundation, missiles are the refinement above them. This is exactly the structure Ukraine created through necessity, and it is now becoming the template for NATO. For Moscow, this is a strategic disaster. Russia's long-range strike doctrine relies on a single premise: force the defender to burn money. But with Skynex, that premise collapses. By early 2025, analysts within Russian institutions, such as Tsesnaya Tokmash and the Zhukovsky Academy, were warning that Russia's low-cost strike strategy was being dismantled. Yet, the problem extends far beyond Ukraine. It lies in the speed at which Europe is industrializing Skynex. Rheinmetall has opened new production lines in Germany, expanded A-head ammunition manufacturing, and begun constructing assembly hubs across Europe to meet demand. Unlike long-range missiles, which require months per batch, 35mm rounds can be manufactured at industrial scale. Europe can expand Skynex deployment far faster than Russia can replenish its stocks of KH-101, KH-55, or Caliber missiles. Every trend line points to a single conclusion. If Ukraine can achieve this impact with a handful of batteries, what happens when Europe fields hundreds? This is the scenario that truly alarms Russian commanders. The supposed invincibility of low-altitude penetration, once considered Russia's asymmetric advantage, is being dismantled by a system they never regarded as a threat. Worse still, they have no equivalent answer. No Russian network gun system, not even Pantsir SM, can match Skynex's combination of cost efficiency and interception rate. But the Skynex effect does not stop at Europe. It is beginning to shape NATO's strategic posture toward Russia, China, and Iran for the decade ahead. And to understand that future, we must look at the next question. What happens when Skynex becomes the standard air defense platform for an entire continent? The future of European air defense and the foundation of NATO's deterrence posture is being reshaped in real time, and Skynex has become the cornerstone of that transformation. Not because it outperforms Patriot or SAMP divided by T in range or power, but because it solves the single most decisive problem modern warfare presents: surviving saturation attacks at the lowest possible cost. Ukraine demonstrated that a single Skynex battery can alter the defensive outlook of an entire city. The question confronting Europe is simple. If one battery can do that, what happens when 50 or 100 are deployed across the continent? According to internal NATO assessments from early 2025, the answer is blunt: Russia would lose the low-altitude strike advantage it once regarded as untouchable. Once Ukraine's layered defense model is scaled to continental size, the entire low-altitude corridor along the domain of Caliber, KH-101, and KH-55 becomes a kill zone. Patriot and SAMP, divided by T, secure the highest tier, shielding critical infrastructure. IRIS-TSL and NASAM screen the middle layer, filtering major threats. And at the lower tier, Skynex, upgraded Gepards, and the mobile Skyranger 35 form a dense barrier against subsonic missiles and unmanned systems. Beneath them, Manpads teams and mobile drone hunters complete the mosaic. In this architecture, Skynex is the load-bearing layer, the system that determines whether the network collapses under economic pressure or endures. Without it, every NATO country would be forced to spend tens of billions of euros each year firing medium-range missiles at cheap drones, decoys, and low-cost cruise missiles, an economically catastrophic model. This realization triggered a continent-wide industrial shift. Germany expanded AHEAD ammunition production. Switzerland increased machining capacity for 35mm systems. Eastern European states began stockpiling shells at wartime levels. Within NATO planning documents, Skynex is no longer treated as an auxiliary system. It is now considered a mandatory pillar of every defense plan for the years leading to 2030. Leaked strategic material indicates that NATO is modeling a new architecture, the European Air Defense Grid 2030, a unified C4 ISR network in which one nation's radar feeds another nation's gun battery, allowing the entire continent to function as a single integrated organism. In this model, Skynex forms the backbone of the close-in defensive tier. Not glamorous, not headline-grabbing, but essential, the structural layer upon which everything else depends. For Russia, this is not merely a challenge, it is a strategic crisis. The entire concept of low-altitude penetration, refined over 20 years to force opponents to burn money, is evaporating. When a multi-million euro Caliber missile can be shredded by a burst of ammunition costing a few thousand euros, the cost equation of modern warfare is reversed. No longer small loss for large damage. Now it is large loss for zero damage. Russia has no equivalent. Panzer SM, despite improvements, is not a distributed sensor network. Tunguska is outdated. Tor M2 is too expensive and lacks the ammunition depth for massed raids. None of Russia's systems can replicate the cost per kill symmetry that Skynex achieves. And the Skynex effect does not stop at Europe. It is now shaping NATO's approach to China and Iran. Wargame simulations in the Taiwan Strait and the South China Sea reveal the same conclusion. The alliance cannot rely solely on missiles to defeat swarms of drones, radar decoys, and subsonic cruise missiles. A low-cost, precise, rapidly reloadable, highly scalable defensive tier is essential. According to analysts at RAND and CNA, that tier is Skynex and the Skyranger family. For Ukraine, this shift marks the beginning of a new chapter. OSENT reporting suggests Kyiv may already have received undisclosed Skynex batteries alongside new crews trained in Germany and Switzerland. As Skyranger 35 enters service with mechanized brigades, Ukraine will gain a mobile shield capable of moving with offensive operations, something Russia has almost no counter for. Every rail junction, strategic bridge, and logistics hub will be reinforced by a density of air defenses unseen in modern European history. This leads to the final, strategically decisive question. If Ukraine can shoot down Russia's best cruise missiles with 35mm guns, what happens when all of Europe fields hundreds of such systems? The answer is simple and unforgiving for Moscow. The strategic advantage Russia once believed was permanent will disappear, not because the defender is more powerful, but because the defender is cheaper, faster, and more sustainable. One small gun, one vast network, one brutally clear lesson: in modern war, victory is not determined by firepower alone, but by the economics of firepower. Near the end of the Second World War, countless Allied pilots recalled the same chilling memory. They were flying in their familiar formation machine guns ready, radar steady, radio links clear, when a metallic blur suddenly ripped past them. It moved so fast that almost no one could turn their head in time to see what it was. It was not a Bf-109, it was not an FW-190. It did not resemble anything the skies over Europe had ever witnessed. And if it had appeared just 1 year earlier, the air map of an entire continent might have been rewritten. It was the Messerschmitt Me-262, the world's first operational jet fighter to enter real combat. But its most terrifying aspect was not merely its speed, it was the entirely new philosophy of air warfare it signaled. No more elegant dogfights spiraling through the clouds, only high-velocity dives, fire and breakaways executed in seconds, where a single miscalculation meant death. The question is, how did a nation being bombed to exhaustion manage to create a machine so far ahead of its time, and why did this so-called miracle weapon ultimately become a military revolution born too early? By the year 1943, Nazi Germany was confronting a brutal reality. Its air force was being crushed in the skies directly above its own territory. America's B-17 and B-24 flying fortresses, alongside Britain's Lancaster bombers, struck in relentless waves day and night, pounding industrial hubs, armament plants, and fuel refineries. The Bf-109 and FW-190 were still lethal in the hands of veteran pilots, but they were now outmatched in speed, altitude, range, and above all, sheer numbers. The Allied strategy of breaking an enemy's war machine from the air was finally working: destroy production before the Wehrmacht could use it. Within this context, the German Air Ministry had to confront a cold conclusion. If they continued relying on piston engine fighters, the Luftwaffe would be decisively defeated in the air war, and once the skies were lost, every effort on the ground would simply be delay and collapse. The question was no longer whether to upgrade, but whether to leap ahead or be erased from the sky entirely. Germany, however, was not starting from zero. Just before the war, the Heinkel He-178, an experimental jet aircraft, successfully flew in the month of August of 1939, proving that jet propulsion was no longer science fiction. In the month of April that same year, Messerschmitt received a formal directive, Project P-1065, a jet-powered interceptor requiring a cruising speed above 530 miles per hour, about 850 kilometers per hour, and a minimum endurance of 1 hour, enough for takeoff, climb, interception, and return before fuel depletion. But technological pressure was only half the equation. Germany was now under full war economy strain. Naval blockades and strategic bombing strangled access to fuel and critical metals. A single Me-262 airframe cost roughly 87,400 Reichsmark. Each Jumo 004 engine added another 10,000 Reichsmark. Armament systems, electronics, and labor pushed the real cost far higher. On the other side of the battlefield, every shot-down B-17 represented a massive American financial loss. The calculation, therefore, was not just about performance, it was about cost-exchange ratio. If an extremely expensive Me-262 could reliably bring down 4-engine bombers packed with explosives and trained crews, it could shift the economics of the war. The operational requirement thus became existential. The Luftwaffe needed a platform with absolute speed superiority to punch through escort fighters, tear into bomber formations, deliver a killing blow in seconds, and disengage before the enemy could react. Existing piston fighters had reached their aerodynamic ceiling. Squeezing extra performance from the Bf-109 or FW-190 offered diminishing returns, while the loss of experienced pilots grew severe. The limits of the old generation were unmistakable. Near transonic speeds, straight wings suffered dangerous compressibility effects, airflow shock, buffeting, and heavy control response, especially during dives. Piston engines, no matter how powerful, remained tied to propeller efficiency, which collapsed at high speeds. Meanwhile, B-17 and B-24 formations were increasingly escorted by long-range fighters such as the P-51 Mustang, capable of penetrating deep into German airspace and even pursuing defenders back to their airfields. The Luftwaffe's once decisive maneuverability advantage was evaporating. Thus, the original design philosophy of the Me-262 emerged. Speed is armor. The aircraft needed to outrun every adversary by at least 150 kilometers per hour, climb rapidly, and carry devastating firepower specifically optimized to shred heavy bombers. In exchange, designers accepted the trade-offs: poor low-speed handling, fragile engines, and reduced pilot friendliness. The Me-262 was conceived not as a multi-role aircraft, but as a strategic interceptor, a weapon intended to fracture the Allied bombing campaign. But the journey from blueprint to combat-ready aircraft was anything but smooth. Immature engine technology, shortages of strategic materials, political interference, most notoriously Adolf Hitler's insistence on turning it into a fast fighter bomber, and chaotic logistics repeatedly delayed the program. By the time the Me-262 finally appeared in the skies in the year 1944, it was both a technological wonder and a symbol of a nation already exhausted. And so a crucial question emerges beneath its elegant aerodynamic shape. How different was the Me-262's internal engineering from everything that came before it? That answer lies in the technical dissection awaiting in the next section. Imagine standing beside a wartime runway as a Messerschmitt Me-262 taxis out for takeoff. A low metal fuselage, a long pointed nose, a single seat cockpit up front, and most striking of all, two engine nacelles hanging like steel warheads beneath each wing. This unusual configuration was not an aesthetic choice, but the product of testing cycles, accidents, and hard-learned engineering lessons. Early in development, engineers intended to place the engines inside the wing roots, as many aircraft designers of the era preferred. On paper, it reduced drag and produced a cleaner airframe, but the risk was fatal. If an engine exploded or shed turbine blades, the high-velocity debris could tear through the load-bearing structure and incinerate the pilot in an instant. Moving the engines into external gondolas solved several problems at once. It simplified wing construction, made engine swaps faster for ground crews, and if disaster struck, allowed most of the blast energy to occur outside the central fuselage. It was a design decision born from a blend of performance, maintainability, and survival. The wings of the Me-262 carried a modest leading-edge sweep of roughly 18 to 20 degrees. At the time, Germany did not yet have a fully developed theoretical doctrine for swept wings and transonic airflow. The original reason for the sweep was practical, balancing the center of gravity to compensate for the heavy wing-mounted engines. Yet by accident, this mild sweep dramatically improved high-speed aerodynamic behavior, reducing compressibility effects and giving the aircraft greater stability in the 800 to 870 km/h range, a regime where piston fighters rarely dared to fly. For the pilot in the cockpit, that gentle sweep could mean the difference between a machine that still obeyed control inputs and one shaking itself apart as airflow piled up beneath the wings. At the heart of the Me-262 were its two Junkers Jumo 004B engines, the world's first mass-produced axial flow turbojets. Each engine used a multi-stage axial compressor, an annular combustion chamber, and a single-stage turbine, producing roughly 1,800 kilograms of thrust. But behind that number lay a brutal compromise. Lacking high-temperature alloys, such as nickel and cobalt, German engineers resorted to low-grade steel for turbine blades. The result was a shockingly short service life, sometimes as little as 10 to 25 flight hours, and with meticulous metal inspections, perhaps 35. The Jumo 004 was in many ways a technological flare, brilliant, powerful, but burning out quickly. Yet its simplicity and inexpensive materials allowed thousands of engines to be built rapidly enough to equip both the Me-262 and the Arado R234. This trade-off only became catastrophic when the war dragged on longer than the designers had hoped, something that by the year 1944 was all but inevitable. Operating the Jumo 004 forced pilots to abandon old habits entirely. Abrupt throttle movements at low speed could cause combustion temperatures to spike, overheating turbine blades, snapping them, or igniting the entire engine. Takeoff and climb procedures were therefore rigid. Throttle up slowly, increase acceleration steadily, avoid sudden transitions, and synchronize both engines at all times. In the cockpit, the pilot constantly watched rotational speed, exhaust temperature, and the engine's delayed response, completely unlike the instant power delivery of a piston engine. The Me-262's airframe used stress-skin duralumin alloy construction with steel components at high stress points such as landing gear mounts and engine supports. Two main fuel tanks of roughly 900 liters sat ahead of and behind the cockpit, with an optional belly tank. We increasing total capacity to nearly 2,000 to 2,470 liters, depending on configuration. This layout kept the center of gravity stable as fuel burned away, but also turned the area surrounding the pilot into a highly flammable zone. Another example of performance taking precedence over protection. Flight controls were entirely mechanical, using cables and levers to actuate ailerons, flaps, and rudder. There was no hydraulic or fly-by-wire assistance of any kind. In high-speed flight, compressibility effects dramatically increased control forces, requiring the pilot to apply significant physical strength and avoid